Hey there, and welcome back to the Deep Dive. Ever feel like primary school maths is a world unto itself, especially as kids get to that final year?
Oh, definitely. It can seem quite opaque from the outside.
Yeah, you hear terms like expected standard, fluency, reasoning, problem solving.
Mm-hmm.
But what exactly does all of that mean in practice? Like, what are pupils really meant to know and be able to do by the end of year six?
Mm-hmm.
And how do those tests, the FATs, actually measure it?
It's a really important question.
Today, we are pulling back the curtain on that crucial stage. We're doing a deep dive into Year 6 mathematics in the UK. What are pupils expected to learn by the end of primary school? How is that measured in those, well, sometimes intimidating end-of-year tests?
And perhaps most importantly, what does it really mean to meet that vital expected standard? What does that actually look like?
Exactly.
It's like getting the blueprint for this key phase of education. Understanding what the official frameworks require is fundamental, not just if you're directly involved as a teacher or parent, but really for anyone who wants to grasp the educational milestones in a child's journey.
Absolutely. And this deep dive isn't based on guesswork or, opinion. It's built on a really solid stack of official sources.
Mm-hmm.
Our analysis draws directly from the statutory curriculum documents published by the Department for Education,
The DFE.
the official assessment framework from the Standards and Testing Agency, the SDA, which tells you how the tests are actually built,
Which is crucial.
and valuable pedagogical guidance from experts like the NCETM and the Education Endowment Foundation, the EEF. So this is a detailed look at the official landscape that defines the end of primary maths.
It really shows the intended path for learning and, I guess, the criteria for judging whether that path has been successfully navigated.
Exactly. So our mission today is to extract the most important, actionable insights from this detailed analysis. We want you to walk away understanding the core aims that underpin all of UK primary maths. The specific objectives Year 6 pupils are meant to master across the different domains. The mechanics of how proficiency is assessed through the SATs, what meeting the expected standard genuinely looks like in terms of skills and capabilities,
Yeah, what it looks like.
and the evidence-based approaches schools can take to help pupils reach that point. Think of this as your shortcut to being genuinely well-informed about a critical milestone in UK primary education. I'm genuinely excited to dig into the specifics here. It feels like we're uncovering the actual recipe for Year 6 maths success, straight from the source.
And year 6 isn't just an endpoint, is it?
Yeah.
The level of attainment here forms the foundation for secondary education. So a clear picture of these official requirements is key to understanding that transition.
Okay, let's unpack this. Before we get into the specific topics and skills Year 6 pupils are expected to master, let's look at the core ideas, the philosophical underpinnings that the UK's National Curriculum for Maths in Key Stage 2 is built upon. The sources really highlight that the curriculum isn't just a shopping list of things to learn. It's structured around 3 central aims that are meant to shape teaching and learning right from the start of primary school.
That's right. The national curriculum provides this overarching purpose to ensure all pupils receive a high-quality mathematics education that equips them for understanding the world, appreciating the subject's beauty and power, and importantly, developing enjoyment and curiosity.
That enjoyment piece is key, isn't it?
Absolutely. It's designed to build a strong command of fundamentals, preparing them for the complexities of secondary school and beyond.
And these 3 core aims, you said they're not separate. What are they and how are they meant to work together?
So the 3 aims are fluency, reasoning, and problem solving. And the sources are very clear. These are interwoven strands. They should permeate all teaching and learning across Key Stage 2, not be taught in isolation.
Right, not like separate lessons on a Tuesday for reasoning and Thursday for fluency.
Exactly, no. It should all be happening together, ideally.
Let's drill down into each one then. First, fluency. The source definition sounds quite straightforward. Varied and frequent practice with increasingly complex problems over time. But what's the insight there? Is it just about being fast?
Well, that definition is a starting point, but the analysis goes deeper.
Yeah.
Fluency isn't just speed or, rote memorization. It encompasses a deep conceptual understanding
Okay.
that then allows pupils to recall and apply mathematical knowledge rapidly and accurately. Think of it like building blocks. You need the blocks, the concepts, and facts readily available in your hand to build complex structures quickly.
Right.
The varied and frequent practice part, especially earlier in a pupil's journey, is crucial precisely because it helps build this automaticity. It
Hmm.
helps pupils become flexible in their thinking, moving confidently between different mathematical contexts and representations.
So it's not just drilling times tables until you can recite them, although that recall is part of it, definitely.
That's part of it, yeah.
It's understanding why 7 times 8 relates to 56, how that connects to 56 divided by 8, and being able to instantly use that relationship in a problem, maybe even seeing it visually or applying it to something like fractions. It's reliable recall underpinned by understanding.
Exactly. That deep understanding and automaticity free up mental capacity, what we sometimes call working memory, which is absolutely vital for tackling more complex tasks later on.
Makes sense. Okay, next up is reasoning, the source definition. Follow a line of inquiry, conjecturing relationships and generalizations, and developing an argument, justification, or proof using mathematical language. That sounds quite advanced for primary school to me.
It does sound quite formal, but it's really about nurturing that mathematical way of thinking from a young age. It means pupils need to be able to make connections between different mathematical ideas, seeing how fractions link to percentages, for instance.
Right.
It involves identifying patterns, making educated guesses or conjectures about those patterns, and then being able to articulate their thought processes precisely. And the explicit focus on using mathematical language is key here.
Using the right words.
They need the right vocabulary and sentence structures to explain how they solved a problem or why their answer makes sense.
Ah, so it's not just getting the right answer, it's explaining how and why. Using the proper maths words, it's developing the ability to build a logical argument in maths.
Precisely. It's about understanding the underlying structure and logic of mathematics, not just performing calculations, thinking like a mathematician, essentially.
And the third aim is problem solving, applying knowledge to a wide variety of both routine and non-routine situations with increasing sophistication. How does that build on the other two?
Well, this is really where fluency and reasoning come together in action, isn't it? It's taking that secure knowledge, the fluency bit, and the ability to think mathematically, the reasoning bit, and using it to tackle genuine problems. This involves skills like breaking down a complex problem into simpler, more manageable steps, figuring out which operations or methods are needed, and demonstrating perseverance when the answer isn't immediately obvious.
So this is where maths stops being just sums on a page and becomes a tool for understanding the world, right? Because real-world problems don't come with a label saying, use long multiplication here.
Oh, no, they don't.
You have to figure that out.
Absolutely. And the curriculum explicitly includes both routine problems, which might be familiar types encountered in textbooks, and non-routine problems, which require more flexible and creative application of knowledge.
You mentioned these three aims are interwoven.
Yeah.
What's the practical takeaway there for teaching and learning? How does that look in a classroom?
It means that, ideally, a maths lesson isn't a silo. It shouldn't just be, say, 20 minutes of practicing a calculation procedure, the fluency in isolation.
Right.
It should involve reasoning about why that procedure works and then applying it to solve the problem solving. They should be taught concurrently, supporting and strengthening each other in a spiral.
Got it. They're the pillars supporting the whole structure of mathematical learning in primary school. Now, the sources also touch on the curriculum structure and flexibility. It says the programs of study are year by year, but schools must teach the content by the end of the key stage.
This is a really important point for understanding how schools operate. While Year 6 has specific objectives associated with it, the statutory requirement is that all the content for Key Stage 2, that's Years 3, 4, 5, and 6, is covered by the end of Year 6.
Right.
This gives schools flexibility. They might introduce some content from the Year 6 program of study in Year 5 if pupils are ready, or conversely, spend time in Year 6 consolidating concepts from earlier years if pupils need more time to grasp them securely.
Okay, so the Year 6 document lists what should be covered eventually by the end of that year, building on everything before it. But schools have some leeway in when exactly it's taught within Years 3, 6.
Precisely. However, the expectation in the curriculum guidance is that the majority of pupils will advance through the programs of study at broadly the same pace.
Broadly the same pace feels like a key phrase, especially when you think about a classroom full of different learners. How does the guidance suggest handling pupils who grasp things quickly versus those who need more time?
The guidance is quite specific on this point, and it's crucial for understanding the mastery approach often talked about. For pupils who grasp concepts quickly, the recommendation is not to accelerate them rapidly onto new content from year 7 or beyond.
Okay, so not just pushing them ahead.
No. Instead, they should be challenged with richer, more sophisticated problems that require them to apply the current year 6 content in more complex or novel ways. This is about developing depth of understanding within the expected curriculum.
I see. Going deeper, not faster.
Exactly. And for those who are not yet fluent or secure with earlier material, they should be given opportunities to consolidate their understanding before moving on to new topics. This might involve targeted support or differentiated activities, ensuring they secure the fundamentals first.
So it's depth over acceleration for the quicker learners, pushing their understanding horizontally, you could say, not just vertically, and securing foundations for those who need more time. That makes sense for trying to keep a cohort moving forward together while still meeting individual needs.
That's the intention, yes. It's about ensuring all pupils build a secure and deep understanding of the core concepts for their year group and key stage, allowing them to access the next stages successfully.
Understanding this balance helps you see why schools focus on ensuring deep understanding of key concepts, why they might spend more time consolidating certain topics, and why securing fundamentals from earlier years isn't just review, it's crucial preparation that enables success in year 6.
Absolutely, it's foundational work.
So with those core aims driving the philosophy and that understanding of curriculum structure in mind, what does this actually look like on the ground? What is the landscape of learning in year 6 maths? Here's where it gets really interesting. Year 6 is truly the culmination of the entire Key Stage 2 curriculum, pulling together everything that came before.
It really is.
The curriculum outlines 6 key domains or areas of mathematics that pupils need to cover.
Yes, and the sources highlight the overall focus for Upper Key Stage 2. It's about extending pupils' understanding of the number system to work with larger numbers, developing the crucial connections between multiplication and division, and how they relate to fractions, decimals, percentages, and ratio.
Okay.
There's a strong emphasis on mastering formal written methods for all 4 operations, and then applying all of this knowledge to solve a wider range of increasingly complex problems. And as you mentioned earlier, Year 6 is notably where algebra is formally introduced, initially as a tool for problem solving.
Okay, let's walk through these domains. Number sounds like the foundational one, and the sources confirm it's the largest and most heavily weighted.
It is, by far. And within number, there are 3 main strands they focus on: number and place value, addition, subtraction, multiplication, and division, often just called calculations,
Right.
and fractions, decimals, and percentages, or FDP as it's sometimes shortened.
Let's start with number and place value. What's expected by the end of year 6? We're talking big numbers now, right?
We are. They need to work with significantly larger numbers than before. This includes reading, writing, ordering, and comparing numbers up to 10 million, and understanding the value of each digit in those numbers.
Wow, 10 million.
Yeah. They must be able to round any whole number to a required degree of accuracy, like rounding 3,456,789 to the nearest 100,000, for example.
Okay.
The curriculum also introduces negative numbers in context, such as understanding temperature below 0,
Makes sense.
and calculating intervals that cross 0 on a number line, like finding the difference between 5 degrees Celsius and mid at 2 degrees Celsius. These skills are then applied to solve problems involving these larger numbers and concepts.
So understanding big numbers and dipping below 0, that's a definite step up, getting ready for the number lines they'll see in secondary school.
Exactly. Next, the calculation strand. This is about mastery of the 4 operations. They need robust mental calculation strategies, including with mixed operations and larger numbers. But a key focus is on formal written methods.
The long multiplication and division stuff.
Exactly. They must be able to multiply multi-digit numbers specifically, up to 4 digits by a 2-digit number, using the formal method of long multiplication. For division, they need to divide numbers up to 4 digits by a 2-digit number, using both formal long division and short division where appropriate. And a key part of this is interpreting remainders correctly based on the problem's context. Sometimes it's a whole number remainder, sometimes it needs to be expressed as a fraction or decimal, or sometimes the context requires rounding the result up or down.
Interpreting remainders in different ways.
Yeah.
That adds a layer of practical application beyond just getting a quotient and remainder, doesn't it?
It really does. It requires understanding the problem. They also need to identify common factors, common multiples, and prime numbers up to 100, and use their knowledge of the order of operations, often remembered with acronyms like BODMAS or BIDMAS, to carry out calculations correctly.
Ah, floater miss, bid miss. That rule that tells you whether to do the multiplication or the addition first, in a sum like 2 plus 3, 4. Why is knowing that specific order important?
Well, it's essential for getting the correct answer when a calculation involves more than one operation, isn't it? Without a standard order, different people would get different answers.
Right, chaos.
Pretty much. BIDMIS, brackets, orders, indices, division, multiplication, addition, subtraction, or BUDMIS just provides that clear rule. Do things in brackets first, then powers or indices, then division and multiplication working from left to right, and finally addition and subtraction also left to right. It ensures mathematical communication is unambiguous.
Got it. It's about consistency.
Ah.
And all these calculation skills are then applied to solving multi-step problems.
Yes. They must be able to solve problems requiring 2 or 3 steps, deciding which operations and methods to use and why. And a crucial check on whether their answer is reasonable is using estimation beforehand.
Estimation is such a practical skill. It catches silly errors and builds number sense.
Right, it builds mathematical intuition. Now, the fractions, decimals, and percentages subdomain is notoriously extensive and requires deep, flexible understanding, building significantly on year 5.
Like really flexing between all three formats, FD and P.
Absolutely. They must use common factors to simplify fractions, like changing 68 to 34, and common multiples to express fractions with the same denominator, like adding 13 and 14 requires changing them both to twelfths.
Right.
This allows them to compare and order fractions, including those greater than 1. They need to add and subtract fractions with different denominators and mixed numbers, again, using equivalent fractions. They are required to multiply simple pairs of proper fractions, for instance. Calculating 14 of 12 is the same as 14 multiplied by 12, which equals 18.
Ah, the O's means multiply there.
Yes. They also need to divide proper fractions by whole numbers, such as figuring out what 13 divided into 2 equal parts is, which is 16.
So operating on fractions themselves, not just finding fractions of quantities.
That's a key step up. And a critical connection they need to make is associating a fraction with division to calculate decimal fraction equivalence. For example, understanding that the fraction 38 is the same as the sum 3 divided by 8, which equals 0.375.
Right, seeing the fraction bar as a division sign.
Exactly. In decimals, they must identify the value of digits in numbers up to 3 decimal places and confidently multiply and divide numbers by 10, 100, and 1,000, giving answers up to 3 decimal places.
So shifting digits around the decimal point.
Precisely. They also multiply 1-digit numbers with up to 2 decimal places by whole numbers, like calculating the cost of 8 items at Porio 65 each, and use written division methods for answers with up to 2 decimal places. Finally, they must rapidly recall and use equivalences between simple fractions, decimals, and percentages, like knowing that 0.5 is 12 and 50%, and apply this knowledge in various contexts, for example, comparing quantities given as percentages.
Phew. That is a lot in fractions, decimals, and percentages. It sounds like they need to be truly fluent in switching between those representations and seeing the links.
Exactly. It's about understanding there are different ways of representing the same proportional value. That flexibility is key.
Okay, moving beyond number, which is clearly huge, ratio and proportion. This is formally introduced in year 6, right? Though they've touched on related ideas before.
Yes, it builds on earlier exposure to multiplication and division relationships, but it's formalized here. Pupils must solve problems involving the relative sizes of 2 quantities, where missing values can be found using integer multiplication and division facts.
Like those for every there are type problem.
Exactly. They need to calculate percentages of measures, like finding 15% of 360 grams, and use percentages specifically for comparison. They also solve problems involving similar shapes, where the scale factor is known or can be found, like scaling a recipe or reading a map.
Practical stuff.
Very. And solve problems involving unequal sharing and grouping, using their fraction and multiple knowledge.
The source mentions the non-statutory notation A.B and gives that recipe example. For every egg, you need 3 spoonfuls of flour. It makes it feel very practical.
It is practical. Understanding ratio is fundamental for many real-world applications and, higher-level maths later on.
Next, algebra. Also formally introduced in year 6. That feels like a significant step up. Is it scary for them?
It can be, but it's introduced gently, primarily as a way to represent and solve problems they might have already encountered. The statutory objectives include using simple formulae, for example. If the rule is add 5 and multiply by 2, maybe writing that as n plus 5, 2, or using a formula for area that they've learned.
Okay, using letters to represent numbers.
Yes. They need to generate and describe linear number sequences, sequences that increase or decrease by the same amount each time. They must express missing number problems algebraically, using letters or symbols like those find x problems.
Right.
They also need to find pairs of numbers that satisfy an equation with two unknowns, for example, finding possible pairs of whole numbers a and b, where a plus b equals 10, or where a multiplied by b equals 24.
Exploring possibilities.
Exactly, and enumerate all possibilities of combinations of two variables, like figuring out how many different pizza combinations you can make with 3 crusts and 4 toppings.
So using letters to stand for numbers, identifying patterns, and figuring out possibilities. It's the very beginning of using symbols to generalize and solve problems more efficiently.
Yes, the non-statutory guidance clarifies it's about using symbols and letters to represent missing numbers, lengths in geometry, coordinates, angles, and just generalizing patterns they observe. It's a tool.
Measurement is next. What are the specific Year 6 requirements there? More complex conversions.
Yes, pupils must solve problems involving calculation and conversion of units of measure, often using decimal notation up to 3 decimal places now. This includes converting between standard units of length, mass, volume, and time, going both from smaller to larger units, like grams to kilograms, and vice versa.
Okay.
A specific practical requirement mentioned is converting between miles and kilometers.
A real-world conversion. Good
Get
one.
paid. In geometry-related measurement, they need to recognize that shapes can have the same area but different perimeters, and vice versa, a classic problem that tests understanding of the concepts, not just calculation.
Right, that distinction is important.
They must recognize when it's possible to use formulae for area and volume, and specifically calculate the area of parallelograms and triangles.
Area of parallelograms and triangles. How is that typically approached? Is it building on rectangles?
Yes. Often, the formula for a parallelogram's area, which is base times perpendicular height, is often shown to derive from rearranging it into a rectangle.
Yeah.
And a triangle's area is then often taught as half the area of a corresponding rectangle or parallelogram, half base times height. This connection helps build conceptual understanding rather than just memorizing isolated formula.
So it's not just memorizing formulas, it's seeing the relationship between the shapes.
Exactly, linking it back to geometry and multiplication division. Finally, they calculate, estimate, and compare the volume of cubes and cuboids using standard units like cubic centimeters and centimeters and cubic meters, extending to include cubic millimeters and cubic kilometers.
So getting into 3D space and volume calculations, proper spatial stuff.
Yes, building towards more complex spatial reasoning and practical application like capacity.
2 more domains. Geometry. What's covered here?
Geometry is split into properties of shapes and position and direction. For properties of shapes, pupils must be able to draw 2D shapes accurately using given dimensions and angles.
Using protractors and rulers properly.
Yes, and recognize, describe, and build simple 3D shapes, including understanding and constructing their nets, the 2D pattern that folds into a 3D shape.
Nets are always fun. Bit tricky sometimes.
They can be. They compare and classify shapes based on their properties and sizes, number of faces, edges, vertices, types of angles, parallel lines, etc., and find unknown angles in any triangles, quadrilaterals, and regular polygons.
Finding missing angles, like knowing if 2 angles in a triangle are 60 and 70 degrees, how do you find the third? Using that 180-degree rule.
Precisely, using the fact that angles in a triangle add up to 180 degrees. They also need to know the parts of a circle radius, diameter, circumference, and the relationship that the diameter is twice the radius.
Okay, basic circle terminology.
And crucially, they must recognize angles where they meet at a point, which add up to 360 degrees, angles on a straight line add up to 180 degrees, or angles that are vertically opposite are equal, and use these facts to calculate missing angles in diagrams.
Those angle facts are absolutely foundational for later geometry, aren't they?
They really are. For position and direction, pupils must describe positions on the full coordinate grid, meaning all 4 quadrants, including negative coordinates like -3, 5.
So not just the top right corner anymore.
No, this builds on earlier work in the first quadrant. They must also draw and translate, which means slide simple shapes on the coordinate plane and reflect or flip them in the axes, both the x and y axes.
So shapes moving around and reflecting across the origin point. Definitely expanding their spatial mapping skills into negative territory.
Precisely. It's a big step.
And finally, statistics. What's the focus here?
This domain focuses on data handling and interpretation. Pupils must interpret and construct pie charts and line graphs and use them to solve problems. Line graphs are particularly important for showing changes over time, trends. Okay. They also need to calculate and interpret the mean as an average for simple sets of discrete data.
Can you quickly explain discrete data again?
Sure. Discrete data is data that can only take certain values, often whole numbers, like the number of siblings someone has. You can't have 2.5 siblings or the swore on a die roll. It's distinct, countable values.
Got it.
This contrasts with continuous data, which could be any value within a range, like height or temperature. So calculating the mean for discrete data means finding the average of a set of distinct numbers.
Got it. Thanks. The source also notes that the non-statutory guidance connects angles, fractions, and percentages to pie charts. That makes sense.
Yes, showing that a pie chart sector might represent 25% of the data, which is also a quarter. And in a full 360-degree circle, that sector would have a 90-degree angle. It's
Okay.
another example of those interwoven concepts we talked about.
Right.
They also need to understand when using the mean is appropriate as a measure of central tendency, as opposed to perhaps the median or mode in some situations, although the focus here is mainly on calculating the mean.
Wow, that is a genuinely comprehensive curriculum. It covers a huge amount, building year upon year. It's clearly not just about numbers anymore by year 6.
It really is the culmination of primary maths, requiring pupils to integrate knowledge and skills from across the whole of Key Stage 2.
That's a comprehensive curriculum covering 6 key domains and 3 overarching aims. But how is all this knowledge and all these skills actually measured, particularly for those high-stakes accountability purposes at the end of primary school? The primary tool is the Key Stage 2 SATs. Let's break down these tests.
Right. The SATs are the main mechanism used to measure pupil attainment against the national curriculum expectations and to provide data on school performance at the end of primary. They are specifically designed by the Standards and Testing Agency, the STA, to assess what pupils have achieved in relation to those curriculum objectives we just discussed.
Okay, so what's the practical setup? How many tests are there for maths? How long do they take? What's the format like?
Okay. The PS2 mathematics assessment consists of 3 separate papers. They are administered nationally over 2 days in May, usually towards the end of the school year. The total testing time across the 3 papers is 110 minutes.
Okay, just under 2 hours total.
And there are a total of 110 marks available across those papers, so roughly 1 mark per mite, although obviously some questions take longer than others.
And a crucial detail the sources emphasize, no calculators are allowed in any of the maths papers.
That is absolutely key. It means that computational fluency and accuracy are being tested directly, even within the problem-solving and reasoning contexts. Pupils must be able to perform the necessary calculations themselves. No safety net.
All right, let's look at each paper individually. Paper 1 is arithmetic. What's that like?
Correct. Paper 1 is 30 minutes long and is worth 40 marks. Its sole focus is to assess pupils' confidence and fluency with standard calculations. The questions are deliberately context-free, just sums or calculations presented numerically.
Like 1234 plus 567 or 45 by 67.
Exactly, and they require a constructed response, meaning the pupil writes the answer down. Most questions are worth 1 mark, but the questions requiring formal written methods for long multiplication or long division are worth 2 marks.
So they get marks for showing the method too, potentially.
Yes, they reward the correct procedure as well as the final answer in those cases.
So paper 1 is purely a test of whether you can perform the core calculations accurately and relatively efficiently under timed conditions.
Yes, it's a direct measure of procedural fluency. Nail those methods.
Papers 2 and 3 are the reasoning papers. What's the difference there?
Both paper 2 and paper 3 are 40 minutes long, and each is worth 35 marks. So 70 marks in total for reasoning. The focus here is broader bone. They assess a blend of fluency, problem-solving, and reasoning skills.
Okay.
The questions are presented in a wide range of formats, including multiple choice, true-false, matching, questions requiring pupils to show their working or provide a justification or explanation.
So more varied question types.
Much more varied. And crucially, these questions are often set within a context, requiring pupils to read, interpret information from text, tables, charts, or diagrams, figure out the mathematical steps needed, perform the necessary calculations, and present their answer clearly.
So paper 1 is checking the calculation engine, but papers 2 and 3 are checking if you can use that engine to navigate real-world or at least context-based problems and explain your thinking sometimes.
That's a great analogy. Paper 1 assesses the computational skill. Papers 2 and 3 assess thinking like a mathematician, which aligns more directly with those broader curriculum aims of reasoning and problem solving we talked about earlier.
This structure makes it clear that the assessment is trying to measure different aspects of mathematical proficiency, isolated skill, versus applied understanding. It's not just one thing.
Precisely. They're trying to get a rounded picture within the constraints of a test.
Now, here's where it gets really interesting, and honestly, it's one of the most significant findings from our sources. The official content domain weighting in these tests.
This reveals a very specific priority, doesn't it? It does. It's quite eye-opening. The Standards and Testing Agency publishes a test framework that specifies the approximate weighting of marks across the different curriculum domains we just discussed. This weighting is not equal across all domains, and that's a critical insight.
So some areas get way more marks than others.
Way more. For assessment purposes, the 6 curriculum domains are grouped into 2 superdomains.
And the weighting is quite dramatic, right? What are the numbers?
It's very significant. The first superdomain, which bundles together number, ratio, and algebra, accounts for approximately 75–85% of the total marks available across the 3 papers.
75 to 85%.
Yeah.
Just from number, ratio, and algebra.
Yes. That means between 83 and 93 marks out of the total 110 come from these areas. Number and place value, calculations, fractions, decimals, percentages, ratio and proportion, and algebra.
Wow. 3/4 to over 4/5 of the entire assessment is focused on number-related concepts and their immediate extensions. That's a huge slice.
It is enormous. The second superdomain, measurement, geometry, and statistics, accounts for the remaining 15–25% of the total marks.
Just 15 to 25% for all of measurement, geometry, and statistics put together.
That's right, between 17 and 27 marks out of 110, covering measurement, geometry, both properties and position direction, and statistics.
So while the national curriculum lists 6 domains as equally important pillars of a broad and balanced maths education, the high-stakes assessment is overwhelmingly weighted towards number-related proficiency.
Absolutely. An analysis of past papers consistently confirms this. Calculations and fractions, decimals, and percentages, FDP, are always the most heavily represented topics within that dominant first superdomain.
Really? Even within that big chunk?
Yes. The sources mention that in the 2024 papers, the calculations domain alone, just addition, subtraction, multiplication, division, accounted for a remarkable 41% of the questions.
41%. Just for calculations. That's almost half the marks available from just that one specific area within number.
Yes. It was the highest proportion seen historically, apparently. This stark evidence highlights a strategic tension for schools, doesn't it?
Definitely. How do you dedicate sufficient time and focus to delivering the full, rich curriculum, which includes measurement, geometry, and statistics as important areas in their own right, while also ensuring pupils are highly proficient in the number, ratio, and algebra content that dominates the assessment?
It's like training athletes for a pentathlon, but knowing that 80% of their final score will come from just 2 events. You want them to be well-rounded, but you have to heavily prioritize those key events if you want them to score well.
That's a very good analogy. A school that teaches a perfectly balanced curriculum, giving equal weight to all 6 domains, as perhaps the curriculum's philosophy might suggest, could potentially see their pupils underperform in the SATs compared to a school that strategically prioritizes deep, relentless practice in number skills.
And the risk then is that focusing too much on the test's weighting might lead to less time being spent on other important areas of maths that are valuable for real-world application or future study, even if they aren't tested as heavily. It's a real balancing act.
So what does this all mean for you, listening? It means understanding that while your child will learn about shapes, graphs, and measurements, the vast majority of their measured attainment in the SATs will come from their ability to work confidently and flexibly with numbers, fractions, decimals, percentages, ratio, and basic algebra.
Yeah. Schools must and do prioritize deep understanding in these areas because it's key not only for the test, but because, as we discussed, fluency and understanding in number are foundational and enable access to concepts in measurement, geometry, and statistics anyway. You need number skills for almost everything else.
True.
And it's not just about what they know, but how they think mathematically. The test framework also outlines a cognitive domain, making explicit the types of thinking skills required in the assessment.
Okay, beyond just knowing the maths facts, what kind of thinking is being assessed? How do they measure the how?
Well, paper 1, the arithmetic paper, primarily assesses procedural fluency. As we said, it's testing accuracy, efficiency, quick recall of facts, and the correct application of standard methods. Because the questions are context-free, it has a lower cognitive load. You just perform the procedure.
So can you do the sum correctly and efficiently? That's the main cognitive skill there.
Essentially, yes. Papers 2 and 3, the reasoning papers, are designed to assess higher-order thinking, conceptual understanding, and mathematical reasoning. As we discussed, these questions are often contextual,
Right, the wordy ones.
requiring pupils to interpret the problem, identify the mathematical steps needed, plan a strategy, execute the calculations, and often show or explain their working.
They require more brain power, interpretation, and strategy than just paper one.
Definitely. The varied formats in these papers probe a range of specific cognitive skills. These include applying known facts and procedures to unfamiliar or different situations, interpreting information presented in various formats like charts, tables, diagrams, and written text.
Reading the question properly is key.
Absolutely. Making connections between different mathematical ideas within a problem, and being able to communicate a line of reasoning or justify an answer, sometimes using precise mathematical language.
So paper one is a check on calculation mechanics. But papers 2 and 3 are assessing whether you can use those mechanics, understand the ideas behind them, and apply them to figure things out, really. Assessing thinking like a mathematician, like you said before.
Precisely. They require pupils to not just perform procedures, but to understand the mathematical structures involved, make connections, and articulate their thinking process.
Why does understanding this cognitive aspect matter to you, the listener? Because it shows that doing well in the SATs isn't just about being fast and accurate at sums in paper one, although that's important, obviously.
40 marks worth.
Right. It's equally about your ability to apply that knowledge, think critically about problems, interpret information presented in different ways, and be able to communicate your mathematical ideas effectively, papers 2 and 3. It's a broader skill set.
It really is.
So, we've covered the curriculum's ambitious scope, the structure and revealing weighting of the SATs tests, and the cognitive skills they aim to measure. But how is success truly defined? What does that crucial expected standard everyone talks about really mean in the end? Is it just a certain number of marks?
Well, the marks feed into it, but the expected standard is the official judgment determining whether a pupil has demonstrated sufficient knowledge, understanding, and skills in relation to the key Stage 2 curriculum by the end of primary school.
Okay.
It's a key piece of information shared with parents and secondary schools, and it's used for school accountability measures as well.
How is that standard determined from the test scores then? How do they get from marks to expect?
Okay, so pupils receive a raw score first. That's simply the total number of marks they achieved out of the possible 110 across the 3 papers.
Straightforward enough.
This raw score is then converted into a scaled score. The scaled score system runs from 80 at the lowest end up to 120 at the highest.
Why do they use a scaled score system instead of just the raw score or percentage? What's the point of that?
It's primarily to ensure fairness and comparability year on year. The difficulty of the tests can vary slightly each year, despite efforts to keep them consistent.
Ah, okay.
So a standard-setting exercise is conducted after the tests each year, involving teachers and assessment experts to determine what raw score corresponds to the key scaled score benchmark for that particular year's test papers. This ensures that achieving the expected standard represents the same level of underlying mathematical performance, regardless of minor variations in test difficulty between years.
Right, so getting 60 marks might be expected one year, but maybe 62 marks the next year if the test was slightly easier. The scaled score adjusts for that.
Exactly, and that benchmark for the expected standard is always.
Always 100. A scaled score of 100 is the magic number. A scaled score of 100 or more means a pupil has met the expected standard for the end of Key Stage 2.
Right. 100 is the threshold.
So what about scores below or above 100? What do they mean?
A scaled score of 99 or below means the pupil is judged as working below the expected standard. A score from 100 up to 109 is working at the expected standard.
Okay.
And a score of 110 or above is classified as working at greater depth within the expected standard, sometimes described as having exceeded the expected standard.
So greater depth is essentially meeting a higher standard within the primary curriculum scope, showing a really strong grasp.
Yes, demonstrating mastery beyond the basic threshold.
The sources give us some context here. In 2024, 73% of pupils nationally reached the expected standard in maths, and the average scaled score nationally was 104. It also notes that the raw score needed to achieve that scaled score of 100 has historically been around 51–55% of the total available marks.
Yes, that gives you a sense of the pass mark range in terms of raw scores. It's typically just over half the marks needed to reach that scaled score of 100. But the scaled score is the official measure used for reporting and comparison.
Okay, so the scaled score is the quantitative measure. But the courses also talk about performance descriptors. This sounds like the qualitative definition describing what a pupil at this level can actually do rather than just their score.
Exactly. These are rich, qualitative descriptions developed by subject specialists and teachers. They're not designed as a tick list for teachers to use for assessment in the classroom. That's important.
Right, and not a classroom checklist.
No. Their primary purpose is to help set the standard for the test itself during development and marking, and to provide a detailed picture of the typical characteristics, knowledge, and capabilities of a pupil who is performing right at the threshold of the expected standard. So someone scoring bang on 100, essentially.
So they describe the abilities and knowledge a pupil at this specific benchmark, the cusp of passing, usually possesses.
Yes. A pupil working at this threshold is judged to have demonstrated sufficient knowledge and skills to be successful in the next phase of their education secondary school. They should be able to engage with all types of questions on the tests, although they may not always achieve full marks on the most complex multi-step problems or those requiring extensive written reasoning. They might make some errors on the harder stuff.
Okay, that makes sense. Let's dive into the detailed profile based on the source's synthesis of these descriptors.
Yeah.
What does meeting the expected standard actually look like across the different areas of maths we discussed? What can a pupil at the standard typically do?
Okay, let's synthesize the profile from the sources table of descriptors, trying to make it concrete. In number and place value, a pupil at the threshold can confidently use place value up to 1 million and are developing confidence with numbers up to 10 million. They can round any whole number accurately to the nearest 10, 100, 1000, or any power of 10. They understand and can use negative numbers in practical contexts like temperature and calculate intervals crossing zero on a number line. They can also generate, describe, and complete linear number sequences that count up or down in steps of any whole number that has one significant figure, for example. Sequences going up in nines, down in 20s, or up in 3000s. Simple, consistent steps.
Secure with place value for large numbers, rounding, basic negative number concepts, and simple sequences.
Got it. Right. In calculations, for operations, they can perform mental addition and subtraction with numbers up to two significant figures, like calculating 95 plus 36 mentally. They use formal written methods, like column addition subtraction, reliably for whole numbers with more than 4 digits.
Okay.
They can use their times tables knowledge up to 12 by 12 and place value understanding to multiply and divide mentally, for instance, calculating 60 times 70, knowing 6 by 7 is 42. They can multiply numbers up to 2 digits by a 2-digit number using formal long multiplication.
Okay, standard long multiplication.
Yes. They can divide numbers up to 4 digits by a single-digit number using formal short division, and they are noted as becoming confident with long division for 2-digit divisors.
Becoming confident with long division by 2 digits is a specific phrasing that suggests it's not necessarily a fully automatic skill yet at the standard, maybe.
Yes, it implies they are capable, they can follow the steps, but it might still require concentration, or they might make occasional errors. It's not necessarily effortless yet. They can also recognize and use multiples and factors of numbers, prime numbers less than 20, and square numbers up to 144, 12 squared.
Okay. What about fractions, decimals, and percentages? This area felt particularly dense in the curriculum overview. What's the benchmark here?
A MEP pupil at the expected standard can recognize and use equivalent fractions, for instance, understanding that 45 is the same as 8100. They know and can use the equivalences between simple fractions, decimals, and percentages, like knowing 0.3 is equal to 330%. They're not necessarily expected to know obscure conversions.
Right, the common ones.
They can add and subtract fractions that have the same denominator, or where one denominator is a multiple of the other, like adding 14 and 58, because 8 is a multiple of 4. This is a key distinction. They aren't necessarily expected to add fractions with completely unrelated denominators, like 23 plus 35, which requires finding a lowest common multiple at this threshold standard.
Ah, okay. So fraction addition subtraction is expected mainly when the denominators are hopefully related. That simplifies it somewhat.
It does focus the expectation. They can find simple fractions and percentages of whole number quantities, such as calculating 23 of 90 or finding 30% of 60 pounds. They can add and subtract decimal numbers with the same number of decimal places and multiply a one-digit decimal number by a single-digit whole number, like 0.68.
Okay, so operating with FDP in fairly straightforward scenarios.
Precisely. In ratio and algebra, they can solve problems using simple ratio to compare quantities thinking about relative sizes. They can estimate distances on maps using simple scales. They can use simple formula expressed in words, such as following a rule to calculate cooking time based on weight. They can find possible values in missing number problems with one or two unknowns. For example, listing pairs of whole numbers that add up to 10, a plus b equals 10, or multiply to 24, ab equals 24.
Simple ratio, using rules expressed in words and basic algebraic thinking with unknowns, starting points.
Yes. For measurement, they can read, write, and convert time between analog and digital 12-hour and 24-hour clocks and calculate durations. They can convert between adjacent metric units of length, capacity, and mass, like converting between kilograms and grams. 1.2 kilograms equals 1,200 grams. They can calculate the perimeter of compound shapes, those L shapes made of rectangles joined together, and the area of squares and rectangles.
Time, basic metric conversions, and area perimeter of familiar shapes. It seems practical.
Right. In geometry, they can compare and classify 2D and 3D shapes based on their properties, how many sides, angles, faces, edges they have. They can recognize and describe simple 3D shapes from their nets.
Okay.
They can use key angle facts, knowing angles around a point add to 360 degrees, angles on a straight line add to 180 degrees, and angles in a triangle add to 180 degrees to calculate missing angles in diagrams.
Using those core angle facts.
Yes. They can describe positions on a 2D coordinate grid in the first quadrant, positive x, positive y, and are becoming confident with using all four quadrants, including negative coordinates.
Becoming confident with 4 quadrants, again showing they are starting to apply it, but perhaps not completely fluent or error-free yet at this threshold. But those angle facts are a solid expectation.
Correct. Finally, in statistics, they can complete, read, and interpret information presented in tables, bar charts, line graphs, and simple pie charts. They can also calculate the mean as an average for simple sets of discrete data.
Interpreting common graph types and calculating the mean, basic data handling.
Yes. And critically, across all these domains, they demonstrate developing problem-solving and reasoning skills. They can solve routine mathematical problems that require 2 or 3 computational steps involving any of the 4 operations. They can begin to reason mathematically, making simple generalizations and using mathematical language to explain their thinking.
Begin to reason, suggesting it's developing, not fully polished yet.
Exactly. They can use and interpret mathematical symbols and diagrams correctly and present mathematical information clearly.
So, looking across all those points, this isn't just a list of topics they've been shown. It's a profile of practical mathematical ability. A pupil at the expected standard can do things with the maths they've learned. Apply it, explain it, figure things out, at least in familiar contexts.
Absolutely. It's about functional mathematical literacy at the end of primary school. And when you synthesize all these detailed descriptors, the source identifies key overarching competencies that truly define what it means to meet this standard.
What are those key competencies that summarize this level of proficiency? What does it boil down to?
Okay, first, secure procedural fluency. This means they have a reliable command of the standard written calculation methods and can perform mental calculations accurately. This fluency is crucial because it frees up their working memory.
Freeing up working memory. That's a great way to put it. If the calculation takes all your brain power, you have none left for the problem itself.
Exactly. If they don't have to concentrate hard on how to do a multiplication sum, they can use that brain space to think about what the problem is asking and the overall solution strategy.
Makes perfect sense.
What's next? Second, application of knowledge. They can take the facts and procedures they know and apply them correctly to solve routine problems that are presented in different contexts, problems that aren't just bare calculations. They can extract the essential information from a worded problem and identify which operations are needed.
So they see the maths embedded in a situation, not just in a textbook box. They can translate it.
Right. Third, making connections. The pupil at this standard is starting to see how different mathematical ideas link together. For example, they can use their understanding of fractions and percentages to interpret a pie chart, or they see how place value helps with multiplying decimals. They see it as a connected subject.
Seeing the connections makes maths feel like a coherent subject, not just isolated rules to memorize. That's powerful.
Precisely. Fourth, mathematical communication. They understand and use standard mathematical language, symbols, and diagrams correctly. They can interpret data presented in tables, charts, and graphs, and they can present their own results or working clearly.
Being able to talk about maths, read graphs, and show your work clearly, that's important for both learning and application, isn't it?
It is. And finally, fifth, developing resilience. They can tackle problems that require multiple steps to solve, holding those intermediate results in their memory and persevering through the process to find the final solution, even if it takes a bit of effort.
Multi-step problems definitely require persistence. You can't give up after the first calculation if you get stuck.
Yes. These 5 competencies, fluency, application, connections, communication, and resilience, are the building blocks not only for doing well on the test, but for future mathematical learning and for using maths effectively in the real world. Meeting the expected standard means a pupil is developing these crucial skills.
Okay, if that's what the standard is, what does the analysis of the sources tell us about how schools and pupils actually get there? What does the research and expert guidance say about effective teaching approaches for Year 6 maths?
Yeah.
How do they build those competencies?
Well, the most crucial overarching message that comes through from sources like the NCETM and EEF guidance is that achieving the expected standard in Year 6 is the culmination of a pupil's entire primary mathematics education.
Right, you mentioned this earlier.
It's absolutely not just about intensive preparation or cramming in Year 6. It requires a coherent, well-sequenced curriculum that builds deep understanding cumulatively over time, right from the very beginning of primary school, from reception onwards.
So success in Year 6 isn't some kind of last-minute magic trick. It's the result of strong foundations being laid consistently from reception through to Year 5. You can't suddenly get good at maths in the last year.
Exactly. The Year 6 assessment relies heavily on secure knowledge and fluency built in earlier years. A pupil can't successfully add fractions with different denominators in Year 6, for example, if they don't have a secure grasp of finding equivalent fractions from Year 5. It just won't work.
That makes total sense. You can't build the top floor of a building if the lower floors aren't stable and complete.
Precisely. The guidance also talks a lot about building foundational fluency, but as we discussed with the themes, it emphasizes that this goes beyond just rote learning or memorizing procedures without understanding. That kind of learning is described as brittle.
Brittle, meaning it breaks easily under pressure or when applied differently.
Exactly. It doesn't transfer well. So what strategies do the sources highlight for building this kind of robust fluency that's linked to understanding?
Yeah, what works?
A core strategy is emphasizing mathematical structures, helping pupils understand the why behind the how. For example, when teaching the formal written method for long multiplication, don't just say put a 0 here. Explain that the 0 is a placeholder because you're now multiplying by the tens digit, which is 10 times bigger. So the result needs to be shifted 1 column to the left, representing multiplication by 10.
Understanding the place value behind the steps in the algorithm makes it much less likely you'll just forget a step or put the 0 in the wrong place.
Exactly. Using physical resources like place value counters or visual representations like diagrams alongside the abstract algorithm helps make this understanding concrete.
Okay.
Another key strategy is prioritizing the automaticity of core facts, rapid recall of number bonds, and, crucially, multiplication tables up to 12 by 12. The insight here, supported by cognitive science, is that this automaticity is essential for freeing up a pupil's working memory.
There's that working memory link again. It's like having your basic tools instantly accessible so you can focus on the complex task, the actual problem.
Yes. If they have to spend cognitive effort calculating 7/8, they have less mental capacity available to interpret the worded problem, decide on the multi-step strategy, or engage in reasoning. This automaticity needs consistent, targeted practice throughout primary school, not just rushed attempts in Year 6, little and often.
Right. And what else?
And finally, using varied and frequent practice. This is central to a mastery approach. Pupils encounter concepts in multiple contexts, using different representations like bar models, number lines, or part-whole diagrams, which builds a deeper, more flexible understanding than just doing pages and pages of the same type of sum mechanically.
Okay, so building calculation skills alongside a genuine understanding of why they work, using varied practice. What about cultivating reasoning and problem-solving skills, which are assessed in papers 2 and 3? These require more than just calculation. How do you teach those?
Yeah, this needs explicit teaching, not just assuming pupils will pick it up by osmosis. Strategies highlighted include teaching metacognitive skills, teaching pupils to consciously plan their approach to a problem, monitor their thinking as they work through it, does this still make sense, and evaluate whether their final answer seems reasonable.
Thinking about your own thinking.
Exactly. A powerful, practical way to model this is for teachers to use a think aloud strategy, verbalizing their own thought process as they solve a problem in front of the class. Okay, first I need to understand what the question is asking. This looks like a two-step problem. I'll calculate this first. That kind of thing.
So making the thinking process itself visible to the pupils, not just the final answer.
Precisely. It helps pupils internalize the kinds of self-questioning they should be doing. Another strategy is developing precise mathematical language. Pupils need the correct vocabulary to articulate their reasoning clearly and unambiguously.
Using the right math words.
Yes. The DFE guidance encourages using specific sentence structures, like, I know that because, therefore, to help pupils structure and connect their mathematical ideas logically when explaining.
That gives them a framework for explaining their logic, doesn't it? Instead of just rambling.
It does. Using models and representations is another powerful strategy, especially for reasoning and problem solving. Visual tools like the bar model can really help pupils understand the structure of a word problem.
The bar model seems incredibly versatile for visualizing different problem types, fractions, ratio.
It is. It helps make the relationships clear, making it much easier to translate the words into a mathematical approach and choose the right operation.
Right.
And finally, teaching problem solving itself as a specific skill set, not just giving problems to solve at the end of a topic. This involves exposing pupils to a wide range of non-routine problems they haven't seen before, and explicitly discussing different strategies they could use. Draw a diagram, work backwards, look for a pattern, try a simpler case, helping them build up a repertoire of problem-solving approaches.
Not just drill and practice, but teaching them how to approach unfamiliar challenges, giving them tools for tackling the unknown.
Exactly. The sources also discuss the importance of proactively addressing common barriers and misconceptions that pupils might develop along the way.
How can schools do that effectively? What does the guidance suggest?
Using assessment for learning is key, not just assessment of learning at the end. This involves using formative assessment throughout the year, looking closely at pupils' work, maybe analyzing errors pupils make on practice papers or in classwork.
Okay.
This question-level analysis, often abbreviated to QLA, helps identify common errors or deep-seated misconceptions, both for the class as a whole and for individual pupils. This data should then directly inform subsequent teaching and revision, allowing teachers to target specific areas of weakness or misunderstanding.
Using assessment data to pinpoint where the learning gaps are and adjust teaching accordingly. Makes sense.
They also highlight the need to explicitly focus on what the NCETM calls squeezed concepts.
Squeeze concepts, what are they?
These are topics like geometry and statistics, which, as we saw from the assessment weighting, get fewer marks and can sometimes receive less curriculum time due to the sheer volume and assessment importance of number work.
Right. The ones that make up the smaller slice of the SAT's pie.
Exactly. However, these areas are still assessed in the SATs, and they are important mathematically. Schools need to ensure these domains are planned for and taught thoroughly, not just rushed at the end or skipped over if time runs short.
Acknowledging that strategic tension, we discussed balancing curriculum breadth versus assessment depth and making sure nothing important falls through the cracks.
Yes. Another strategy is ensuring interventions are tightly connected to classroom teaching. Any targeted support program for pupils who need extra help must be explicitly linked to what's being taught in the main classroom.
So not just sending them off to do something completely different.
No. It should pre-teach concepts before the main lesson, address specific identified gaps related to current topics, or consolidate understanding of classroom learning, but it should never be a disconnected, isolated experience. It needs to be coherent for the child.
Keeping that support aligned with the core curriculum makes sense.
And finally, fostering positive attitudes towards mathematics. While the evidence base for specific strategies here is still developing, it's widely recognized as an important factor. Schools should work to promote enjoyment in maths and help pupils develop a growth mindset.
The idea that you can get better with effort.
Exactly. Where they see challenges and mistakes not as indicators of failure or not being a math person, but as opportunities to learn and strengthen their understanding.
Attitudes definitely matter in tackling a subject like maths. If you think you can't do it, you probably won't try very hard.
They do. But pulling everything together, the analysis confirms that the most impactful strategy for raising attainment at the end of year 6 isn't any single one of these teaching techniques, but rather a whole school strategy. Tell us more about why that's the ultimate key. Why the whole school?
The clear message is that Year 6 SAT's results are fundamentally a reflection of the cumulative journey throughout Key Stage 1 and Key Stage 2, not just the work done in the final year. The assessment measures knowledge that relies heavily on secure understanding built consistently from year 1 onwards.
Right.
As we said, year 6 content is the top floor, and you can't build it if the lower floors aren't stable. You can't suddenly teach fractions in year 6 if the foundations of multiplication, division, and place value from earlier years aren't secure.
So the real success isn't a quick fix in year 6. It's a sustained effort over 6 or 7 years of primary school.
Exactly. Therefore, the most impactful strategy for improving outcomes at the end of KS2 is to invest in a whole school, coherent, progressive curriculum map that carefully sequences learning year on year, supported by high-quality professional development for all staff teachers and teaching assistants across all year groups, not just year 6 teachers.
So everyone is singing from the same hymn sheet, building consistently. Yes. This shifts the focus from short-term, reactive intervention in the final year to a sustainable, long-term strategy of building deep mathematical proficiency right from the moment a child starts primary school.
That's a powerful and logical conclusion. It makes it clear why strong maths teaching in earlier years is so fundamentally vital for year 6 success. It really is a marathon, not a sprint, with each year building towards that final point.
Absolutely. It underscores the importance of consistent, high-quality teaching throughout.
And there you have it. We've taken a deep dive into UK Year 6 maths, starting with the ambitious aims of the National Curriculum Fluency, reasoning, and problem-solving, exploring the comprehensive scope of skills expected across the 6 domains.
Which is quite a lot.
It is, breaking down the structure and revealing weighting of the high-stakes assessment towards number, clarifying the detailed definition of what it really means to meet that all-important expected standard through the performance descriptors.
Getting beyond just the score.
Exactly. And finally, looking at the evidence-based pathways schools can take to help pupils succeed, emphasizing that it's a cumulative journey built year upon year across the whole school.
Meeting the expected standard, as defined by those performance descriptors, is clearly a multifaceted achievement. It signifies a pupil has developed secure procedural fluency, the ability to apply their knowledge to routine problems, the capability to make connections between different mathematical ideas, confidence in communicating mathematically, and developing resilience in tackling multi-step problems.
It's clear that Year 6 success is the culmination of that long, consistent journey built brick by mathematical brick from the start of primary school.
A testament to sustained effort and quality teaching throughout the key stage, ideally.
So here's a final thought for you to consider, building on everything we've discussed. We spend quite a bit of time on the tension between the broad goals of the curriculum, those 6 domains and 3 aims, and the significantly narrower focus of the high-stakes assessment, which, as we saw, heavily weights number, ratio, and algebra.
That's 75-85% weighting, yeah.
How do you think this imbalance influences what schools feel pressured to prioritize in their teaching? And given that, what do you think is the single most crucial skill for a Year 6 pupil to develop by the end of primary school, beyond just getting a certain score? What truly sets them up for the future?
It's a fascinating challenge for schools, isn't it? Balancing the broad educational mandate with the specific requirements of accountability measures. Which skill do you think is paramount for future success? Problem solving, reasoning, number sense.
Lots to think about there. Thank you for joining us for this deep dive into Year 6 UK Maths. We hope this look at the official blueprint, the assessment realities, and the definition of success is giving you a much clearer picture of what's involved.
Thanks for tuning in. Hope it was useful.
We'll catch you next time for another deep dive into the source material.